So I believe you studied about the theory behind spanning tree protocol and EtherChannel.
Mm.
Yeah, because spanning tree protocol is just a theory, but when we come to EtherChannel, we just do configuration. So if I can just open um, this document here. So spanning tree protocol is just a way of preventing loops in a layer 2 network. So what is a loop? For example, when we look at this topology here, we have switch 1, switch 2, switch 3. Whenever switch 2 sends a message to switch switch 1 sends a message to switch 2, that message will go directly to switch 3. And switch 3 will still send back the message to switch 1. And when the switch 1 receives the same message, it will send to switch 2. And that will be a loop. It will just be going around without a stop, because a switch will be forwarding the same frame every time it receives it. And how to prevent this, we implement what is called spanning tree protocol. So spanning tree protocol will put some ports on forwarding state while some on blocking state, such that when switch 1 sends a message to switch 2, then switch 2 wants to send to switch 3, then it will find that this port is blocked. So the message will not be going all around creating a loop.
But it will be from switch 2 to switch 1 to switch 3.
Sorry?
Oh, I mean, the communication will be going from switch 2 to switch 3 via switch 1, or it will just be blocked, because I can see the connection between switch 2 and the 3 is the one which is blocked.
Well, now the communication will be one way. This will be the path for every traffic, because this one is blocked. So no traffic will be passing through this link because it's blocked. So all traffic will be going from switch 3, switch 1 to switch 2, and from switch 2, switch 1 to switch 3. So let me just put a simple topology here and demonstrate how spanning tree protocol works. So in this small topology here, how will spanning tree protocol work? Spanning tree protocol will put one port in blocking state. For example, let's just wait until all of them turns green and we see which one will be orange. Okay, so this one has been put into blocking state, meaning no traffic can go through this link to prevent loops. Yeah. So for example, this switch here, switch 0 sends a message to switch 2. Switch 2 will not be able to send it out because this port is closed. Yeah. And when this message goes to switch 1, switch 1 will try to send it here, but it will find this port is closed. So that message will die here. So it will not it will not traverse the network endlessly. And that's why spanning tree protocol came to solve that problem, because there's a problem where you can send a message and that message goes around all the switches endlessly until all the switches goes down. So that's what you don't want in this scenario, and that's why spanning tree protocol was implemented. So as you can see, spanning tree protocol blocks some ports on switches with redundant links to prevent broadcast storms and ensure loop-free topology. With the spanning tree protocol in place, you can have redundant links between switches in order to provide redundancy. Okay, so for example, in this topology, spanning tree protocol has placed one port on switch 3 in the blocking state. That port will no longer process any frames except spanning tree messages. If switch 3 receives a broadcast frame from switch 1, it will not forward it out the port connected to switch 2 because this port is in blocking state. So how do spanning tree protocol works? Spanning tree protocol basically has an algorithm that's called spanning tree algorithm that is used to create a topology database of the network. It knows which port to put on blocking state and it knows which port to put on the forwarding state. So condition in spanning protocols. All switches need to select a root switch. For example, on this topology here, these switches participate in a debate and they need to select a root switch. And that root switch, all of its ports are put in forwarding state. Okay. All other switches cannot called non-root switch because they have selected a root switch. Now all of them are now called non-root switch, and they determine the best path to get to root switch. For example, in this topology here, this is our root switch, and this switch 1 and switch 2 has to determine the best path to reach the root switch. Now the best path is this one and this one, this one and this one, the path to the lower cost to reach the root switch. Yeah, and on the shared Ethernet net segment, the switch with the best path to reach the root switch is placed in forwarding state. That switch is called designated switch, and the port is known as designated port. That's what I've just been demonstrating here. This one and this one are put in forwarding state. And also all other interfaces are placed in blocking state and will not forward frames. So for example, this one, it's in blocking state and it will not forward frames. So if I just go down, just for this scenario, let's say switch 1 is selected as the root switch, this one, this is the root switch, and all the ports in switch 1 are in forwarding state. Now switch 2 and switch 3 need to choose the ports with the lowest cost to reach our root switch, and those ports should be this one and this one, the ports with the lowest cost. These ports are put in forwarding state. They are in forwarding state, as you can see, and on the shared Ethernet segment between switch 2 and switch 3, port this one on switch 3 on switch 2 is as the lower port FA0/1 on switch 2 as the lower cost to reach the root switch. This port is placed in forwarding state, but to prevent loop, FA0/1 on switch 3 is put in blocking state. So it's just like what I did here. This one is put in blocking state to prevent loop, so that the traffic cannot be going just this way in a circle. Yeah. So if I can just go ahead, there's something that we call bridge protocol data units. Well, the bridge protocol data units are just messages that are used in spanning tree protocol. So it's the bridge protocol data unit that is used to make the switches communicate about the spanning tree protocol and make them elect their leader, which is the root switch. And inside the bridge protocol data unit, we have root switch ID, the sender switch ID, the sender root cost, hello, messages, maximum aging, and the forward delay timers. Okay. Now let's get to electing a root switch. We understand how we can elect a root switch. Yeah. So the election is based on what is called bridge ID. Bridge ID basically means IDs of the switches, and each switch that participates in STP have 8-byte switch ID that comprises of the following field: 2-byte priority field and 2-byte system ID. The priority field by default it's always been 32768, and the value can be changed based on your configuration. And the 6 byte system ID is always the MAC address. So basically, root switch is selected based on the priority of the switch or the MAC address of the switch. Okay, so a switch with the lowest bridge ID will become a root switch. For example, a switch with the lowest priority will become the root switch, or the switch with the lowest MAC address should become the root switch. So by default, all the switches have the same priority of this one. And the second comparison that should be made is the switch with the lowest MAC address. So in this topology here, we say that by default, all these switches have the same priority of 32768. But now what factor now do we use to choose the root switch? Now we choose the switch with the lowest MAC address, because if I just if you just look at this diagram, you will realize that this is the switch with the lowest MAC address, because it's our root switch, and the root switch, all of its interfaces are put in forwarding state, and every switch is connected to this root switch to an interface that is in forwarding state. Yeah. So this is our root switch, and if I can just go back here, yeah. Then next, selecting a root port. So we are saying that all other switches. So we are saying that all other switches are now called non-root switches, because they have selected their leader, which is a root switch. I mean, now they are all called non-root root switches. Now they
are called like only the switch one A1 will be like a switch. The rest will be none.
Well, in this topology, only this switch will be the root port. So this one and this one are non-root switches.
Yeah.
Because you have one leader, so your members, it's just scenario. That scenario. So all other switches that are now called non-root switches determine the best path to get to the root switch, and the port used to reach the root switch is placed in forwarding state. The best path is the one with the lowest cost to reach a root switch. So let's come here. This is our root switch, and these are our non-root switches. We are saying that the best path to reach the root switch is the root port, and is placed on forwarding state. For example, on this switch, it has two paths. The first path is directly, and the second path is going to this switch, then coming to this switch. Meaning this one is higher cost, but this one is low cost, just directly. So it chooses this one as the low cost. Also for this non-root switch, it has two paths to reach our root switch. The first path is going through switch 2 to this one. The second path is directly, meaning this is the lower cost. Now this is the root port, and it's put on forwarding state. Spanning tree protocols are a little bit challenging. It's very intense. It has a lot of things that you should study and know about. Okay, so also so consider the switch 3 perspective of choosing a root port. Switch 3, this is our switch 3. Two paths are available to reach the root switch. Two paths, and one direct over FA0/1. So this is our root switch. This is the root switch, and switch 3 here wants to reach the root switch. The first path is direct, the second path is going through switch 2, then coming to switch 1. Meaning this one has the lower cost. So this port is the root port. And in case the best root cost ties for both two or more paths, the following tie breaks are applied. we check the lowest neighbor bridge ID, we check the lowest neighbor port priority, we check the lowest neighbor internal port number. But basically what normally we use here is the cost. Okay, so selecting designated ports, selecting on the shared Ethernet segment, the switch with the best path to reach the root switch is placed in forwarding state. The switch is called designated switch, and its port is known as the designated port. So, for example, this thing is becoming more interesting. We say that this is our root switch, and the two of them are non-root switches. And now another concept is coming that is called designated switch. A non-root switch can become a designated switch. So it's non-root switch, which is the biggest category, and under the biggest category of non-root switch, we have designated switch. So how does designated switch comes in? Well, you check on the switch that has all its interfaces in forwarding state. That's the designated switch. So here we have three switches. We have the root switch, designated switch, and non-root switch. Although all of the two are non-root switches, but this is a non-root switch which is designated switch. Spanning tree protocols a little bit challenging, but you could have done this prior to this. So, for example, the designated switch is determined based on the following criteria. The switch with the lowest cost to reach the root becomes the designated switch. In case the time the switch with the lowest bridge ID becomes the designated switch. So, for example, we were saying that by default, the priority of these switches is the same. But now, what do we use to choose a root port? We use a switch with the lowest MAC address. So let's say this switch here is the switch with the lowest MAC address. Then it follows with this one. Let's say this has a MAC address of let's say even .1, and this has .2, and finally this has .3. So the one with the lowest MAC address is our root switch. Then the one that follows is our designated switch, and finally we have non-root switches. Okay. Yeah. Okay. So then under spanning tree protocol, also we have a similar protocol that is called rapid spanning tree protocol. You know, there's something that we call transitioning stage of a spanning tree protocol. For example, when I delete this port here, this link here, and reconnect it again, you can see it's still green, and it takes time to turn to it's still orange, and it takes time to turn to green. That's transition time. We call them states. We have spanning tree protocol port states. So in rapid spanning tree protocol, just the name suggests rapid. It happens very, very fast. It doesn't stay where how can I say this? It doesn't stay like this one stays, because this one stays like around 30 seconds until this one can turn green. But for rapid spanning tree protocol, it happens very, very fast within, let's say, 20 seconds to 15 seconds to 20 seconds. So as the name suggests, it was introduced to replace spanning tree protocol, and it has a standard of this one. And the difference with the spanning tree protocol, we find that rapid spanning tree protocols enable faster convergence times than spanning tree protocol. So that's what I was saying, that whenever we connect a link, it will happen very, very fast without taking too much time. And also, spanning tree protocol features as two port types, root and designated port. But in rapid spanning tree protocol, we add four ports roles, which is root, designated port, alternate, and backup. Okay. So in this topology here, in order to avoid loops, rapid spanning protocol has placed one port on switch 3 in the alternate state. The port will not process or forward any frame except rapid spanning tree protocol's messages. However, if the root port on switch 3 fails, the alternate will rapidly become the root port and start forwarding data. So it's kind of just a rapid spanning tree protocol. It happens very very fast. It allows faster time convergence of of um, of the states. Just a minute. So, are you there?
Yeah.
Okay, okay. So that's the concept of rapid spanning tree protocol, and it just works like spanning tree protocol. But now the difference comes when it allows faster time convergence. It happens very very faster. Yeah. So you can also look at this rapid spanning tree protocol port roles, the status, and how to by default. Let's say by default they are all enabled, and by default the spanning tree protocol is enabled, but you can replace it with rapid spanning tree protocol using this command, spanning tree mod to rapid pvst, which is very very simple. So that's all about spanning tree protocol and rapid spanning tree protocol. Although spanning tree protocol is always enabled by default, so we don't need to configure it. And our main topic today was to configure the EtherChannel or link aggregation. So maybe if you have any question about spanning tree protocol or rapid spanning tree protocol, so that I can explain to you. Because we see that in spanning tree protocol we have only two ports. We have root port and designated port. But in rapid spanning tree protocol we have a root port, alternate port, designated port, and disabled port. And also port status. This applies to all. Port status applies to all. A port is either disabled, blocked, it's in listening state, it's learning state, or in forwarding state. So a port in this disabled state is currently disabled on the port. I mean the spanning tree protocol is disabled on the port. A port in the blocking state states that a port is currently blocked and it cannot forward data or traffic or landmark addresses. A port in the listening state cannot forward traffic and cannot learn MAC addresses. Port in learning state cannot forward traffic, however it can learn MAC addresses. And finally, a port in forwarding state will do everything. It can learn MAC address and forward data. Okay. So basically, our main concern today is EtherChannel. Although spanning tree protocol is very important, but you know it's enabled by default, so you don't need to configure them. But at least you should understand the theory behind spanning tree protocol, how it's the definition, the port roles, the states, how it works, and how the routes, the ports are selected, how the switches are selected. It's very very important. Okay. So today, this was our main topic today, and I believe I asked you to read about spanning tree protocol and a little bit of EtherChannel, so that when I come we just go directly to the practical part. So
Okay.
link aggregation protocol. I'll go back to packet test and do something. Okay, so this was my discussion. This was my discussion. This is the topology that I'm going to use to explain what we mean by link aggregation or EtherChannel. So EtherChannel is a technology that is used to bundle together the physical interfaces into one logical channel. Remember, by default, these interfaces, although from this switch 1 to switch 3 there are 3 interfaces, but it's only one link that is operational. Data can only go through one link. For example, from this switch 1 to switch 3, it will only use the upper link. You can see the two links are orange. Also here, from this one to this one, it can only use one link because of spanning tree protocol. But between this one and this one, this link are nullified because it will create loops. We don't want a scenario where there will be a circle, endless packet moving around the network. So this one is nullified. Also between this one, you can see there's only one link that is used that can transfer data at one time. Yeah. So to enable maximum, to allow maximum usage of all the links, we do what is called EtherChannel. We bundle them together into one logical channel. We assume that they belong to one logical channel, and you won't be able to see these green indicators. So let's go back to the description. EtherChannel allows multiple physical links to combine into one logical channel, and a maximum of 8 links can be aggregated to form one logical link. So at one point, we can bundle together 8 physical links into one logical channel, so that we can use them to transfer data at the same time to maximize the bandwidth. Full link utilization. We don't want links to stay idle. So that also increases redundancy, because when one link under the logical channel is down, then the other links will carry on the data transfer. So if I go down also, so we see that no wastage of bandwidth, then there's no loop, there's redundancy. That's the advantages. Then there's always, before you do something, there's always a criteria for doing something. Before you can configure EtherChannel, you have to make sure that there are some factors taken into configuration. Both ports should be in the same duplex. Do you understand what duplex is?
Yes.
Do you understand what duplex is?
Nah.
Well, a duplex is a way of sending message. we can have a full duplex or a half duplex. Half duplex is a way that I can send a message, then I wait. It's a one way, you see. But full duplex is two way. You can send, I send at the same time. So they should have the same duplex, same speed, same VLAN configuration, same port mode should be the same access or trunk. Okay, these should be taken into consideration, and I would like you to go through these notes after this class because they are very, very important for your understanding. Then EtherChannel, there are two protocols of configuring EtherChannel. The first one is, I was saying that there are two.
Are you recording?
The recording was in progress long time ago.
Oh.
Yeah. So I was saying that to configure EtherChannel, there are two standards. There are two, protocol that we use. First one is called port aggregation protocol, which is called PAGP, and PAGP is a Cisco proprietary protocol that is used in EtherChannel. Another one is called link aggregation control protocol, which is a standard. Everyone can use it. We can use it for all the devices. But for PAGP, we use only for Cisco devices. And in PAGP, we have we have modes. For example, we have a horn mode that will be part of EtherChannel but cannot negotiate the opposite interface to take part in EtherChannel. Another mode is called desirable mode. Desirable mode will be part of EtherChannel, and it continuously tries to convert the opposite side to become the part of EtherChannel. Then we have also auto mode. Auto mode will become the part of EtherChannel, but it cannot negotiate or convert the opposite side to become the part of EtherChannel. Then also finally we have off mode. Off mode, no EtherChannel configured on that interface. Then we need to know the criteria, how to configure them. When you configure EtherChannel on this side, how do you configure EtherChannel on the opposite side? For example, on this topology here, we have switch 1 and switch 2. We have bundled together the two interfaces into one logical channel. So we want to configure EtherChannel on this side, let's say with a desirable mode, and a desirable mode on switch 2 here on this side. Then the EtherChannel will form. Yes, here. Desirable auto. We have configured EtherChannel with the desirable mode with the desirable mode on this side. Then on this side, auto mode. EtherChannel will form. Then auto desirable. Also auto on this side, desirable on this side, EtherChannel will form. But auto, we configure auto on this point, auto on this point, EtherChannel will not form. So you have to take into consideration how to know how to configure both on the opposite sides. You have to use desirable or desirable auto. It's very, very important. Don't use auto. EtherChannel will not form because auto, it will not try to negotiate or convert the other side to be part of EtherChannel. We need a protocol, a mode that tries to negotiate. Yeah. You understand me? Hello?
Hello?
Can you understand me?
Yeah, a little bit.
But
I get lost.
you understand what I'm saying, or still my network is still?
Yeah. But this session, I don't know. I'm feeling I'm tired, but I don't catch the point.
So how will you do this? Can we just explain it now? Then when you come back, we do the practical, because the practical part is the most important part.
Yeah, so I will need to also to read these and so that I can go back on the video so that I can hear well. But for now, today, I don't catch well
Okay.
everything.
Okay. So let me just finish on the LACP, so that when we meet in the next class, then we do the practical part of it.
Yeah.
Okay, so another protocol that we use in EtherChannel is called Link Aggregation Control Protocol. Link Aggregation Control Protocol is a standard. You can use it for Cisco devices, HP devices, Huawei devices, Juniper, etc., etc. So it's a standard EtherChannel protocol that is being used, and most of my configuration I always use LACP. And it also has modes, for example, on, active, and passive, and also off. We say that on mode will try to be part of either channel, but will not negotiate the opposite side to become either channel. Active mode will continuously attempt to convert the other side to form either channel. Passive mode will become part of channel, and it will not try to negotiate or convert the other side to become part of either channel. On mode, no either channel is configured on that interface. Then also here we need to know the criteria of configuration. For example, if we configure active on this side and active on this side, then either channel will form. Active on this side, passive on this side, either channel will form. Passive on this side, active on this side, either channel will form. But passive, it will not form. So you have to mix it. Active, passive, or active, but not passive. Passive, it will not form. So I think that's the end of today's session, and I believe you will go through this so that when we meet again, I can do the practical part of it for better understanding. Hello? Yes, so I'm just saying that that marks the end of today's session, and I believe when you find time, just go through the notes so that when we meet next time, you can have better understanding of the practical aspect.
Yeah.
Yeah, okay, no problem. So let's see you again in the next class.